Yep. Yes, the talk is now recorded, but your faces will not be captured unless you ask a question. And also the coffee break after the talk is not gonna be recorded either. And speaking of questions, um, please feel free to ask questions during the talk. And to do so, you can either send a private message to me or use the raise hand function of Zoom. And then I'll let you ask the question by unmuting you. Finally, if there's any problem or concern during the talk, please contact me via a private message feature. Okay, so now we can move on to the talk. So today we have Abhisekh Sankaran. He's a postdoc at University of Cambridge now, and he's going to talk about extension preservation in the finite and prefix classes of first-order logic. Please start.
Okay. Thanks a lot, Coco. And thanks to you and the organizers for having given me this opportunity to present the work that I've been doing. Am I clearly audible? Is the audio fine? Okay, cool, awesome.
Yep.
Yes, so thanks to the organizers, and thanks also to all of you who have come for the talk. So this work is on extension preservation in the finite and prefix classes of first order logic. This is one of a recent result jointly obtained with Anuj Dawar here at the University of Cambridge. And yeah, I hope to communicate to you the what the result is and how we go about doing it. Yeah. All right. So maybe I'll start. Okay. Now, extension preservation is a well-realized property in computer science. So extension preservation, what is extension preservation? You say a property is extension preserved if it is the case that if you have a model for the property, say you have a graph that satisfies the property, then if you take any extension of the graph, yeah, whereby by extension, where I mean that the extension is such that the graph that you began with is an induced subgraph of your extension, then the extension also satisfies the property. Okay, so for example, if you take a graph containing a triangle, if you were to take any induced supergraph of it or an extension of it, then the resulting extension continues to have a triangle. So having the property of having a triangle is extension closed. In the same way, you can verify that the property of having chromatic number greater than 6 or having clique greater than 10. All of these are extension closed properties. Now, it turns out that one of the earliest results in classical model theory, namely the Los-Tarski preservation theorem from 1954-55, it characterizes first order definable extension closed properties of arbitrary structures, namely structures that are finite and infinite. So it characterizes these properties in terms of very simple kinds of first order logic sentences. These are existential sentences, namely sentences which contain only existential quantifiers and no universal quantifiers. So now the importance of this result is that it constituted one of the first applications of Gödel's compactness theorem from the 30s, and it essentially launched a whole flood of preservation theorems that followed in its wake. So a number of preservation theorems were obtained for properties other than extension closure, such as closure under homomorphisms, closure under surjective homomorphisms, direct products, reduced products, ascending chains, descending chains. So a host of properties were taken, closure under that, preservation theorems for closure under these properties were, under these operations were obtained. And in fact, these investigations even extended not just to, were not just restricted to first order logic, but even extended to infinitary logics. So this was a very active area of research from the 50s to the 70s, mid 70s in classical model theory. And indeed, the subject of classical model theory grew out of these investigations. Now, when the subject of finite model theory began with the work of Ron Fagan, who proved the first descriptive complexity theory result characterizing NP in terms of existential second order logic, it became interesting to ask what happens to these classical preservation theorems and classical results, classical model theoretic results in the finite. And turns out that systematically, most of them fail in the finite. and the Los-Tarski theorem is no exception. It fails in the finite, and this was identified by Gurevich and Shella in 1984, but it turns out that already in 1959, Bill Tait, had already shown the failure of the Los-Tarski preservation theorem in the finite. In particular, he showed an extension preserved first order logic sentence, a first order logic sentence that is extension preserved in the finite, but it is not equivalent in the finite to any existential sentence. So you have an extension preserved first order sentence in the finite that is not equivalent to any existential sentence in the finite. So Tait's example, as we will see, is more powerful than what has been known so far, and we'll look at that. One can ask, given the failure of Los-Tarski's theorem, one can ask, is it the case that first order, after all existential sentences, every existential sentence can be seen as equivalent to an existential sentence in Prinix normal form? Okay, so is it the case that, well, existential sentences in Prinix normal form are not powerful enough to capture first order extension close properties in the finite? But is it the case that if I were to enrich and consider higher prefix classes, then is it the case that there is some prefix class within which I can fit all extension close properties in the finite? Okay, so that's a natural question. And motivated by these, this work is motivated by these questions, and here is what we are able to show. So let sigma n be the class of all first order sentences in Prinix normal form, where the quantifier prefix contains n blocks of quantifiers beginning with an existential block. Okay, so that's sigma n. Pi n is dually defined, where it's Prinix normal form sentences containing n blocks of quantifiers, but beginning with a for all. Now, the first result that we show, and which we will spend a good bit of time in this talk understanding, is that Tait's counterexample is a sigma 3 FO sentence that is known by its very construction. You can see that, but this this sentence is extension closed over all finite structures. So far it is all Tait, but this sentence is not equivalent over the class of all finite structures to any pi 3 sentence. So it is not just existential sentences which are sigma 1. It is not even equivalent to a pi 3 sentence. Okay, and furthermore, this example can be expressed in Datalog. It's a language which I'll tell you about. So again, the counterexample being not expressible in being expressible in Datalog is also an observation made by Weinstein and Rosen. But what we are able to show is that all of these results can be strengthened to show that Tait's example is not even equivalent to a pi 3 sentence. Now we can go further, and we show that for every n, there is a vocabulary sigma n and an FO sigma n sentence varpha n, which is a sigma 2n plus 1 sentence. Okay, so it contains 2n plus 1 blocks of quantifiers beginning with an existential block, such that phi n is extension closed over all finite structures, but it is not equivalent over this class to any pi 2n plus 1 sentence. Okay, and furthermore, phi n can be expressed in Datalog with those two clauses, negation and not equal to. What this summarily means is that no prefix class of first order logic is expressive enough to capture extension closed FO properties in the finite, and FO intersect Datalog queries in the finite. So Datalog queries, they are incomparable. First order logic, there are first order sentences not in Datalog. There are Datalog sentences that are not in first order logic. So the intersection of these two, the class of sentences that it is, this class of sentences is not expressible by any prefix class of first order logic. So this is the object of the talk. So I'll speak to you about these two theorems. We'll spend a good bit of time understanding the first result, okay? Because the second result is a lifting of the same ideas into this more general setting of sigma 2n plus 1. Okay, so we'll spend a good bit of time understanding the first result, which is illustrative in its own right. Okay. Now, analyzing Tait sentence. So this is what we're going to do. We will see the sentence. It's we call the sum total R, for good reason. We will see a Datalog definition of the sentence. So that will show that the sentence is extension closed in the finite. Oh, yeah. So Datalog. So I'll come to that. But Datalog queries, simply by virtue of their syntax, will ensure that the classes that they define are extension closed in the finite. Okay, so a Datalog definition is a proof of the extension closure of sum total R in the finite. We will show that sum total R is not preserved under extensions in the infinite. Because if it was, well, we will explicitly give an example. We will explicitly show an example of how it is not preserved under extensions in the infinite. But even otherwise, if you can see that if it were preserved under extensions in the infinite, then by Los-Tarski's theorem, it would be equivalent to an existential sentence in the infinite. And therefore, it will also be equivalent to the same existential sentence in the finite. And that would contradict Tait's result. But we'll see an explicit example of why this is not preserved under extensions in the infinite. And finally, we'll show the inexpressibility in Pi 3 via the construction of a suitable model and a non-model of sum total R, which bear a certain special relationship between them. Okay. If you have any questions, just feel free at any point in time to ask me. All right. Okay, here is the sentence. So sentence sum total R is basically saying that if the structure is a linear order, and the S relation. So it's a sentence over a vocabulary which contains 3 binary predicates less than R and S. Less than is interpreted as a linear order. S and I'll talk about how R and S are interpreted. So LO less than is a linear order. Partial successor asserts that the relation S is consistent with the successor relation of the linear order, which means that whenever 2 points are related via an S relation, it is indeed the case that they are consecutive in the linear order. Okay, so that's what partial successor says. Which means, so 2 points which are successors could not be related via an S2. So, but whenever they are, then it is indeed the case that S is the successor relation of the linear order. So that's partial successor. The sentence says that if linear order and partial successor, then it is the case that there exists U and V which satisfy the relation called R total. Now R total is the following relation. It is true of U and V if it is the case that there is a back edge, R edge from V to U. And it is the case that for every vertex, for every point which is before U, before V, the point has a successor, has something to which there is an S relation. And therefore, considering partial successor, you would have that point is indeed a successor of the one that you're beginning with. So in the context of finite structures, it means that you can go from U to V via a sequence of S hops. In other words, V is reachable from U via a sequence of S hops. Okay, that's what R total is saying. So in other words, what R total is saying is that V and U, which are the segment which is constituted of V and U, which is identified by this back R relation between V and U, is such that in this segment, the relation S is total. Yeah. So R total is what it is what the sentence is. Now, of course, I've shown this diagrammatically to you, and you must be wondering, well, this is reachability that you're saying from U to V. You're saying this is reachability in S via the S predicates. So how do I know that this is first order expressive? Well, so here is the first order definition. So
okay, sorry, there's a question from Ananthal. If
sure.
you want to ask for yourself, then I'll mute you. It's not working. Oh, sorry, I'll unmute you again. Oh, I'm.
Hi, sorry, yeah, that was exactly my question, to see what is the formula for R total. Please go ahead.
Exactly, sure. So exactly. So, you know, after all, this is reachability, but we observe that this is an ordered graph that we're looking at, right? So here is how we can say this. R total is saying that, first of all, there is a back R edge from V to U. And it is saying that for every Z, which is between U and V, including U, but not including V, it is the case that there is some element ahead of it to which there is an S. Okay. And that element that is ahead of it, of course, since it is ahead, it is not equal to it's not equal to U, but it could be potentially V. Okay, but so for every element there is before V, there is some relation ahead of it to which there is an S edge. And therefore, in conjunction with the previous two sentences, what you have is that this particular S edge would be indeed the successor of, would indeed give you a successor of the point that you begin with. Okay. So that's our total. So we basically leverage the fact that we have a linear order equipped, the structure is equipped with a linear order, and we use that fact. So this is that's the first order definition of R total. Partial successor is easy to say, okay, as described, and then linear order is very standard. So this sentence is indeed a first order sentence. Okay. Now we want to show, okay, here is, to get a feel for it, here is a model for a sum total R. So here is a structure. It is just a linear order on which you have put these S relations, which are indeed successors, and you have these R edges. So linear order is true. Partial successor relation is, of course, again true by construction. And we want to see whether there exists U and V such that they define a segment on which the S relation is total. Well, this is a candidate, but unfortunately, there is the S relation gets broken in the middle. This is another candidate, but the S relation gets broken at the very outset. But here is a candidate which indeed realizes this R total UV property. Okay, so since there exists UV which realize R total, the sentence is sum total is true. Now we want to see the extension closure of the sentence. So here is Datalog. So Datalog rule is of one of the following forms. Rx bar is, it's on the left hand side, and then you have AX1 bar. A is an atom, which in our context will be either x less than or equal to y, or Rxy or Sxy. The atom could also be negated, so you could also have negation x less than or equal to y, and the negations of the other atomic predicates. Okay, so that is one kind of a rule. Another rule is where you have these predicates that you've used on the left hand side. You can utilize them on the right hand side as well, provided it is the case that you do not negate them. Okay, so in the second rule, so Rx bar, the second rule which says that Rx bar is on the left and you have R1 to Rn on the right, these appear unnegated. It is possible for one of the Ri's to be R. Okay, so as a rule, it is only at the atomic level where negations are allowed on the right hand side. Okay, otherwise negations are not allowed. So these are the Datalog rules, and any Datalog program is just a finite set of Datalog rules. Now the semantics of this is very intuitive. So consider the Datalog program, which consists of these two rules. Okay, the first rule taken as a program in itself, it is just corresponds to the sentence which says you take AXZ and BZY and you existentially quantify out Z. I forgot to mention that the free variables of in any Datalog rule, the free variables appearing on the left hand side of the rule are a subset of the free variables appearing on the right hand side. Okay, so therefore, as you can see here in the first rule, and yes,
Abhisekh, there's one question from Alak, so I'll ask. So the question is why are you taking partial successor instead of having a true successor relation by taking the converse of the implication?
You will see why. So why partial successor instead of taking the full successor relation? So we'll see that the fact of it being a partial successor relation is exactly what we will exploit to show a result. Mm-hmm. You just hold on for a little bit. You'll see this very soon. Okay.
Thank you.
All right. So the first rule basically corresponds to the program as I just mentioned here. There exists Z, A, and B. If you take both of these rules together, then this program corresponds to an existential least fixed point logic sentence, which is given as below. So you just try and unpack this. So the second rule is basically saying negation A. So R is such that negation A and R again, but then that R can itself be unpacked again as negation A and R again, and so on. Eventually, you'll hit the base case, which is A and B. Yeah. So you want to, so it's an infinite recursion that is there, and you want to kind of pack it up into a relation that gets built up using this recursion. So that's what the least fixed point quantifier, the generalized quantifier, would allow you to do. Yeah. So you construct this sentence var phi R U V, which which is given as alpha, which is the one that is given above, and or the existential closure with Z of negation A and R again. Okay, so the way you would interpret this is that, okay, you would first start off with R as empty, okay, and then you would get just alpha. Then this is a new relation which gets assigned to R, okay, and then building on that, you can construct, so that becomes the value of R for the next level of iteration, the next iteration, and then you phi R of UV will give you the next R. So it will be alpha UV, or there exists Z, negation AU Z, and the R0 that you computed, or that you computed in the first iteration, and so on. So this whole recursion is packed into this Lindstrom quantifier LFP RUV phi. Okay, so that's an existential least fixed point logic sentence, and Datalog and so therefore every Datalog program corresponds to an existential least fixed point logic sentence, and the converse is also true. Okay, so given this correspondence between Datalog and existential least fixed point logic, and given the fact that any existential least fixed point logic sentence is extension closed, we have that any Datalog program is also extension closed. Okay, so so we will utilize this fact of the very fact that Datalog program by the virtue of its syntax guarantees you extension closure. Okay, so let's see how you can describe sum total R as a Datalog program. Well, it's very natural. So you just express negation LO, negation partial successor, and there exists UVR total as Datalog programs. Okay, and you just take the Datalog program for sum total R is just sum total. There'll be three rules: sum total R, arrow not LO, sum total R arrow not partial successor, sum total R arrow R total UV. Okay, this UV, because there's no free variable on the left hand side, UV gets existentially quantified out, and that gives you exactly what sum total R is as given in the very top of this slide. Okay, let's quickly see any questions at this point. Okay, let's quickly see these definitions. I'm sure you would have already guessed them, but nevertheless, this is linear order. It has a universal definition. You just negate it, you get an existential definition, and the existential definition right away readily lends itself to a Datalog program as shown. Likewise with partial successor, which is also an existential sentence. You can readily write negation partial successor as the Datalog program that is shown here. Okay, now so far it is just first order logic. Okay, where Datalog really comes in is in the last part. Yeah, we have already seen intuitively that we are saying that we are wanting to go from U to V via a sequence of S hops. Okay, so this is only about finite structures. Observe that the sentence really says that between U and V, for every point which is not V, there is a point which is related to it via an S relation. Okay, therefore, when you're looking at finite structures, you will eventually reach V. Okay, so this is an important point here, that this picture is for finite structures. And of course, we are looking at only finite structures here, but this is the important point to note, because when we look at infinite structures, then this is not really the picture. The picture, you would not really be able to reach V, yeah, but you will keep going. So the picture is basically saying that you can keep going, yeah, from you onwards. So this particular relation is naturally expressed in Datalog as this is reachability. So you just need to say that R total UV is just saying that RVU is true, and S reach UV. That means V can be reached from U using the S edges. So either it is the case that U and V are already adjacent via the S relation, or it is the case that from U you can go via the S relation to a point Z, and from Z V is reachable. Yeah, so that's the natural Datalog definition here, and that indeed expresses R total UV exactly. Yeah. So that yeah, and that gives you the Datalog program. Okay. Now let me, yeah. So now yeah. So I think I should yeah. So this shows the extension closure of sum total R in the finite. But this sentence is not extension closed in the infinite, and here is the example. Okay, you have A, which is just natural numbers along with a point at infinity. Okay, and you have the point at infinity comes back to the first, the minimum element of the natural number 1 with the R edge. Then you have the successor relation, the usual successor relation. So basically you can keep going. Okay. B is a structure in which you have 2 points at infinity. You have a back R edge from the last point to the first point, and there is you can keep going whenever you're in the finite, you can keep going to the next point. But in the infinite, from omega to omega plus 1, there is no S edge. First of all, it's easy to observe that A is a substructure of B. You delete this point at omega, you get exactly A. Okay. Now let's verify all the conditions. Linear order, yes, of course, both of them are satisfy that. Partial successor relation, yes, of course, both of them satisfy that again. And here is to the one who asked me the question about partial successor relation, watch. So you have partial successor, which is indeed true. But now R total is true in A. R total is saying that you must have 2 points such that U and V says that there is a edge from B to U. And so that therefore those 2 points must in A be 1 and omega. And now this condition is saying that whenever you are less than omega, you can keep going, which is indeed the case. You have the successor relation which takes you to the next point. But in B, if the only points U and V which satisfy this back R edge is the first is point 1 and point omega plus 1. Okay. So therefore, now you're saying the condition is requiring that for any point before omega plus 1, you can go via an S edge to another point. Now, while that is true of all the finite points, when you come to omega, you have no S edge to go further. Okay. And therefore, because of this, R total is not satisfied in this. Okay. And because R total is not satisfied, but the precondition is you have that sum total R is true in A, but not true in B, despite B being an extension of A. So sum total R is not extension close in the fact. Okay, so that gives you a flavor of why, how we are using the fact that how we are using partial successor relation in a very important way. Okay, so now given the fact that we do not have this extension closure in the infinite, so we cannot use Los-Tarski theorem, how do we show this inexpressibility result in the finite? Well, here is how. So let pi nk. So we want to show that sum total R is not equivalent to any pi3 sentence. So now let pi nk be the class of all pi n sentences in which every block of quantifiers is size exactly k. Okay. So therefore, you can see that every pi n sentence fits into one such subclass. Yeah. So pi n is just the union of pi nk. Now define this relation a n comma k b. I'll just call this a n comma k b. Okay. So the arrow is implied. So a n comma k b is true if it is the case that for every sigma nk sentence theta that is true in A, it is also true in B. Okay, that's the relation. A n comma k b, if every sigma n sentence sigma n comma k sentence that is true in A is also true in B. Oh, I realize that I have not defined sigma n comma k, but sigma n comma k is just defined as the class of all sigma n sentences in which every block of quantifiers is size exactly k. Okay, so that's the condition, and you can see that the same thing can be written using counterpositively can be seen to be asserting that a n comma k b is true if it is the case that for every pi n comma k sentence gamma which is true in A, it is also true in B. Pi n comma k sentence gamma which is true in B is also true in A. Okay, so this is a particular condition which is which will be crucial for us, because what we're going to do is that for every k, we will construct a model mk of sum total R and a non-model nk of sum total R such that nk 3 comma k mk. Okay, which would mean that every pi n comma pi 3 comma k sentence that is true in M must also be true in N. Okay, that means that any pi 3 comma k sentence, if it is a model of mk, it cannot distinguish with, it helplessly is also a model of nk. Okay, but sum total R distinguishes between mk and nk. So this pi 3k sentence could not be equivalent to sum total R, because it is not able to perform this distinction that sum total R does. And since K is arbitrary, for any Pi3 sentence, it is the case that it is not equal to sum total R. Okay. So that is the approach that we would like to take. Okay. And we'll illustrate all the constructions for K equal to 3. At this point, if there are any questions, I'd like to take them. All right. If not, I'll just go ahead. Yeah. So construction of MK and NK, I'll illustrate all the constructions for K equal to 3. So the first, we build up our structures inductively. First, let L8 be this linear order on 8 points. 8 points linear order. S relation is a total successor relation. G8, okay, is the same structure L8 with the middle successor relation removed, with the middle S relation removed. So it's a linear order where you have these 3 hops, but then there is a gap, okay, and the 3 hops again. So that's G8, G for gap. Now gap 3 is the structure which is obtained by, maybe it will be useful to understand Taut 3 first, and then gap 3 is easily derivable from Taut 3. Taut 3 is basically obtained by taking a linear order of length 2 to the 6 first, okay, taking a linear order of length 8 and putting the linear order of length 8 after the linear order of length 2 to the 6 and then pasting them at their ends. Okay, so the last point of L2 to the 6 is identified with the first point of L2 to the 8, L8. Okay, so this operation is what is called ordered sum. We'll see it more formally later on, but intuitively we can see it, already understand it via the picture. Okay, so you take L to the 2 to the 6, you ordered sum it with L8, then you take another copy of L8 and so on till you have taken 7 copies of L8, and then you taken the ordered sum with another copy of L2 to the 6, and then put a back arrow from the first point, from the last point of this constructed structure to the first point of the constructed structure. That is Taut. Okay, so you can equivalently view this structure as one gigantic linear order, which is like of length, which has the number of points in which is 2 to the 6 into 2 plus 8 into 7. So you have so many points, and then you have this back arrow. But it is useful to look at it in this modular way. Okay, we'll again see why. And gap is obtained by taking this. So you have 7 copies of L8 in the middle. You just replace the middle copy with G8. Okay, so that gives you gap 3. Okay, so that's Taut 3 and gap 3 these are the 2 structures that are constructed as shown. Now, using gap 3 and Taut 3 themselves as subroutines, substructures, you construct M and N as follows. You first construct gap 3 plus, which is an ordered sum of 2 to the power 9 copies of gap 3. Okay, and finally you construct N3 as in the same way as you constructed Taut 3. You take gap 3, you take the ordered sum with a copy of gap 3. You do that 7 times, and then you have another copy of gap 3 plus. Okay, so this constructed structure is N3, and in here once again there is a middle gap 3 segment. So you replace the gap 3 with the Taut 3 and you get M3. Okay, that's the construction of these structures. Okay, so it's just hierarchically built. Okay, simple construction, just taking ordered sums, sufficiently large ordered sums whenever you go, as you're going higher and higher, you take sufficiently large ordered sums, and that's all. Okay, now the claim is that M3 and N3 respectively form a model and a non-model of sum total R. Okay, so here is a recap of all these structures, and let's verify all the conditions. Linear order, of course, that's simply by construction. Those individual blocks are linear orders, and you take an ordered sum, so it's a linear order. So both of these structures are linear orders. Partial successor, well, partial successor is again easy to verify. This is simply because of the fact that eventually all of these structures boil down to just L8 and G8. Yeah, and inside L8 and G8, the S relation is indeed a partial successor. Yeah, so cumulatively, the partial successor relationship is true even at the level of M3 and N3. Now, here is R total, and once again we'll exploit the gap that we introduced. R total. If we at all want R total to be true, we must have the first and the last point are related via a back R edge. Now in M3, this back average relation is only true of any segment. Yeah, in M3, or let's say M3. In M3, the back average is true only of each of these segments, gap 3 or tot 3. Okay, so the candidate for U and V must be the endpoints of these of the segments gap 3 and tot 3. Maybe it would be useful if I have this annotator with me. There's no annotator here. I don't see an annotator here. Is there a way by which I can mark on this? This I cannot. I don't see. Is there a way by which? No, I'm not able to see.
No, probably not on Zoom.
I mean, usually maybe on here it is not, but I've otherwise used this. Anyway, no problem. Anyway, I think I have enough this thing, so probably I'll use my markings here. Okay, so R total. So I was just saying that U and V, if R total has to be true in M3, then it must be the case that U and V must be the endpoints of any of these gap 3 or tot 3 segments. Now, given that M3 contains tot 3, if I were to take the endpoints of tot 3 as U and V, then you can see that this is indeed a continuous, there is a full, the successor relation, the S relation is indeed a total relation within this segment identified by U and V. Okay, so because of tot 3, which is total, indeed, as it is, as the name suggests, it is the case that R total gets realized in M3. Yeah. So M3 does satisfy R total UV. But observe that if you were to go to N3, because N3 is just constituted of gap 3 is such that by its very construction, we had this G8 in the middle. And G8 itself is such that it had a gap in the middle. Okay, so the totality of the S relation gets violated inside G8, and therefore inside gap 3, and therefore inside all of N3. So N3 does not satisfy, there exists UV, R total UV. And because it does not satisfy that, but it satisfies the premises of sum total R, it is the case that M3 models sum total R, but N3 does not model sum total. Okay, so here we are, again and again, we are seeing that we are exploiting this fact of the difference between gap and tot. Okay, so we have that now. Now, let's proceed to seeing, so what have we established so far? We have established so far that sum total is a sentence which is extension close, which is in the finite. It is indeed given by a Datalog program. We have constructed a model and a non-model, M3 and N3 of sum total. We constructed a model and a non-model of sum 3 of sum total R. Okay, so we are left with showing that nk, we'll illustrate this for k equal to 3. Nk is 3, k related to mk. If you are able to show this, then it means that every pi 3, k sentence that is true in mk is also true in nk, and therefore the pi 3, k sentence will not be equivalent to sum total R, because sum total R distinguishes mk and nk. Okay, so that's the last part which we want to show, and this is where we.
Yeah. Sorry. Before moving on to that part, there's one question from Prabha. If you want to, okay, sure. I can unmute. I'll unmute the question.
Hi. So, is there anything special about gap 3 in the gap 3? Like, suppose if we take gap 4 or gap 5, is there any difference with that?
Oh, well, actually, I realized that this gap 3, the 3 part of it is really needn't have been there. I could have just called it gap and dot. The gap 3 is just was introduced just when you, so the generalizations that we will see of the sentence in the second part of the talk, they also involve constructing gap structures. So it'll be of the form gap n, k. Okay, so what gap 3 is really is gap 1, 3. Okay, so I basically forgot to remove the 3. So for just understanding Tait's sentence, you don't need the 3. But the 3 really is becomes relevant, or you appreciate the 3 when you see that there are several gaps. Okay, gaps at different levels, and gap 3 was intended to be the gap at the first. Okay, so you can forget the 3 at. All right. Okay, so let me proceed. Yeah, so we want to show this. So now here we are, we have this important game theoretic characterization of this relation, the right arrow, the NK relation. So the NK relation, so here is the game. So you have two players, spoiler and duplicator. And you have a game arena which consists of a pair of structures as opposed to a set of structures, a pair of structures A, B. And you have n rounds. In the odd rounds I, the spoiler chooses a k-tuple AI from A, and in the even rounds he chooses a k-tuple BI from B. In response, the duplicator picks up a k-tuple BI from B in the odd rounds and a k-tuple AI from A in the even rounds. So with this kind of with this choice, with this playing of the spoiler and the duplicator in every round, eventually at the end of n rounds, you would have gotten n k-tuples, and you would say that the duplicator wins the play of the game if it is the case that the map which sends AI to BI is a partial isomorphism between A and B, which means all quantifier-free relationships that are there between the elements of AI and BI and AI and AJ and BI and BJ, those are the same. Okay, so the duplicator wins the play of the game if this partial isomorphism is true, and she has a winning strategy if she wins every play of the game. Now the theorem is just a special case, or is just simply seen from the Ehrenfeld-Frazet theorem, which if you already know, you can appreciate that the duplicator has a winning strategy in the above game if and only if A, N, K, B. Okay, so A and KB is not a symmetric relation, and that is also reflected in the fact in this game because we are considering a pair of structures, and A is the first component of that pair. So that's the EF game characterization of this relation, which we will immediately utilize for our purposes. But before that, I'll just formally define the notion of an ordered sum. We have already seen this. Ordered sum of two ordered structures A and B is just the disjoint union of these two structures in which A appears first and B appears afterwards, and the first and the last element of A is identified with the first element of B. So for instance, you have A and B as shown, then A plus B is exactly the one that is shown on the right. Okay, and in this language of ordered sum, very formally, M3 is just an ordered sum of 2 to the power 9 plus 3 copies of gap 3, followed by the a tot 3, followed by again 2 to the power 9 plus 3 copies of gap 3. Okay, so formally we have seen M3 is just this ordered sum. Right now, we see the following properties that hold of the ordered sum, and this is really these three results are really at the heart of as technical tools. They are really at the heart of the proof. Okay, so here are the properties. If you have A and B, and if you have A, NK, B, then first of all, if you just put this back RH from the last element of A to the first element of A, that structure is NK related to the structure B in which you have this back RH again. Okay, that's a simple this thing. In fact, it's not really a composition property. The composition is really spoken about in the second and the third properties. But this is an important fact which we'll use. The second property basically says if you have structures A1 and B1 with elements little a1 and a2 chosen in A1 and little b1 and b2 chosen in B1, and suppose it is the case that the structure A1, A2 is NK related to B, B1, B2. And suppose on the other hand, if you have two structures A2 and B2 such that A2 with a choice of an element A3, little a3 in A2, is NK related to B2 with a choice of an element B3 in B2. If these two NK relationships are given to you, then if you consider the ordered sum of the structures A1 and A2, okay, and the ordered sum of B1 and B2, then the structure A1 plus A2 with the 3 points A1, A2, A3 chosen in it is NK related to B1 plus B2 with B1, B2, and B3 chosen in it. Okay, this is actually not too difficult to see once you know the game characterization of it, because if you have a game, since you have these NK relations, you already know that the duplicator has a winning strategy in each of these individual games between the two pairs of structures. So you just compose these two winning strategies. In that, if you are playing on A1 and A2, if the spoiler picks up a k tuple in A1 plus A2, then it means that there is a component of that particular tuple which is chosen in A1, there's a component of that chosen in A2. You take the component that is chosen in A1, it is less than a k tuple, so you just pair it up to make it a k tuple by just repeating elements. and you know that that is a choice now in A1. Now you have a winning strategy for the duplicator in the game between A1 and B1, so you can transfer that and pick a k tuple in B1, which respects the padding. Likewise in B2, and then you construct this tuple obtained by joining together the individual tuples obtained. That's all. So that's the second relation. The third relation is that if you take a particular structure and you take the ordered sum of itself with itself sufficiently many times, in particular greater than 2 to the power n dot k times, then any two such ordered sums will be such that they will be related via the nk relation. Okay, and the way to see this for those who already are familiar with EF games and the basic results on this is that if you take two linear orders which are of length greater than 2 to the m, you know that they are m equivalent. Well, this is only for those who are familiar with this. So you just exploit the fact that if you take two large linear orders, they are already m equivalent. This particular ordered sum is really abstracted out as really a large linear order in which every point has been replaced with a. Okay, so the idea of getting a winning strategy in this game is when you make a choice in the top structure, you just look at the choices that are made in the structure abstracted out as a linear order. Okay, now you know that two linear orders are already equivalent. Two linear orders of length 2 to the nk are nk equivalent. So you know that in the other abstracted out linear order, you have a choice of elements. And then you specialize that particular choice by looking at, okay, what is this particular structure? And you go into the structure and make the same choice as made in the other copy of the structure. That's a quick sketch of this particular thing. Okay, so summarily, if you take two large ordered sums, then of the same structure, then the nk relationship between them is true, where the large is depending on one and nk. Those are the three properties, simple to verify. Okay, and they are at the heart of our result. So here, let's begin. We want to show that G8 and L8, the way we constructed them, have this property that G8 is 1-3 related to L8. Okay, so which means that there is a one-round game in the game characterization. There is a one-round game that is played in which the spoiler picks up a 3 tuple. Now the spoiler, let's say he picks up this 3 tuple. If the duplicator just so we look at G8 as composed of these three segments. There is a gap in the middle, then there is the left part of the structure, there's the right part of the structure. These three choices are made from the left part. You just duplicate them, just copy them onto the other structure, and you can see that this choice is a partial isomorphism between G8 and L8. Likewise on the other side, if he picks up elements on the other side alone, then you just copy them in L8. The non-triviality happens when elements are chosen from across the gap. Okay, so you're choosing it from either side. Suppose it is the case that you have chosen elements A1 and A2 on the left side of the gap, but you are not picking up the immediately next element of this gap, but you're choosing an element, any other element after that. You can still replicate the same choice. Okay, you can see that this choice, this copying strategy is still going to work to get a partial isomorphism. So the non-trivial case is when you are choosing the two elements of the gap. Now, if you were to replicate that choice, then there's a problem because there is a gap here, but in the other structure, there is indeed an S relation there. Okay, so just copying now will not help. But here is where we use that this linear order is sufficiently long. So instead of copying, we just shift our choice. So we choose A1 to be B1 as the same as A1, but instead of choosing A2 to be immediately after A1, we just choose it one after. This preserves the property that the linear order relationship between A1 and A2 is true. And it also preserves the fact that A1 and A2 are not successors of each other. This is because of the fact that S is indeed the successor relation in both of these structures. Right? So once we have chosen this one away, then we know that A1 and A2 form a partial isomorphism with B1, B2. But now to choose the element corresponding to A3, we shift once again. Okay, so we go to B3, which is one more which is shifted away, and now we see that this A1, A2, A3 choice indeed has a partial isomorphism with B1, B2, B3. Okay, so this relationship is true between G8 and L8. Let us now bootstrap on this to so that's that. So yeah, since for any choice of a 3 tuple, this relationship holds. You have the 1-3 relation between G8 and L8. Let's bootstrap on this to see the relationship between taut and gap. Taut is, we'll show that it is 2-3 related to gap 3. So that's tot above, and that's gap 3 below. We make a choice. Spoiler goes ahead. He picks up a choice, makes a choice of elements A1, A2, A3 in tot. Now, because tot has sufficiently many copies of L8, in particular, it has 5 central copies of L8. So look at the 5 central copies of L8. You have only chosen 3 elements. You have 5 copies of L8. Definitely 2 will be missed. Okay, so here, these are the 2 copies that are missed. Let us focus on one of those copies. Okay, what we are now going to do is we are now, depending on this choice, we are now going to view tot3 as consisting of 3 parts. First is this middle part, which is this highlighted L8. Then there is a left part of the structure, which consists of this L2 to the 6, L8 and L8. And then there's a right part of the structure, which is these 4 copies of L8 and L2 to the 6. Okay, so this choice gives you a way of splitting up tot3 into 3 parts. Gap 3 has a natural choice split up into 3 parts. Okay, that is that. Yeah, so that's the central part. Then there is the left part, and then there is a right part. Yeah. So we established the correspondence between these 3 parts of tot3 and gap 3. And now what we are going to do is we are going to play the game on each of these parts and then compose them together. Okay, so let us look at just this the left part. We know that in the global choice that was made, A1 continues to stay in this part. Now, this A1 is a large enough linear order. In fact, it's a linear order of length greater than 2 to the 6. And so is B1. Because these two are sufficiently long linear orders, you know that using our composition properties, or even just using using the composition properties, or just using basic results concerning E of games on linear orders, you can see that A1 is 2, 3 related to B1, because 2 into 3 is 6, and we are our linear orders are of length greater than 2 to the 6. So because of this relation, you know that if you were to interpret A1 as being a spoiler move, or rather the tuple A1, 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 a 3 tuple being the spoiler move in A1, in capital A1, then you know that because of this relation, there is a choice of a 3 tuple all of whose components must be the same. Okay, and that choice is available in B1. So let us say that element is B1. Okay, this is such that you can continue this game, okay, for one less round by still ensuring that the duplicator is able to win. In other words, what we're saying is B1 expanded with little b1 is 1, 3 related to A1 expanded with little a1. Okay, so we keep this observation here. Likewise, on the other side, it is the same argument, because these two are linear orders of length greater than 2 to the 6. Once again, you have this 2, 3 relation, and therefore the choice A2, A3 expanded to a 3 tuple. So let's say it's A2, A2, A3, or A2, A3, A3, would have a corresponding choice in B2 as B2 and B3, such that the structure B2 expanded with these 2 elements will be 1, 3 related to the structure A2 expanded with these 2 elements. Okay. And now, what about the central copy? Well, the central copy is exactly G8 and L8, which we just saw a while back, and we had established the fact that G8 is 1, 3 related to L8. This is something that we established. So cumulatively, if we were to put all these parts together, what we find is that each of these parts has a 1, 3 relationship with the corresponding part in the other structure. Okay, and therefore, if we just add them all up, yeah, we do the ordered sum of these, we utilize the composition property of the ordered sum, and we can summarily say that the top structure expanded with A1, A2, A3, and it is related from the bottom structure expanded with B1, B2, B3. Okay. Now, since A1, A2, and A3 were an arbitrary choice in the top structure, and we are saying that for this arbitrary choice, we are able to get a response which gives you the 1, 3 relation. What this means is basically the top structure is 2, 3 related to the bottom structure. And because the top structure is 2, 3 related to the bottom structure, we can use the non-composition property that we saw at the a while back to say that if you just connect the last point of the top structure with the first point, that is 2, 3 related to the same thing done in the bottom structure. But doing this gives you tot3 in the top and gives you gap 3 at the bottom, and so therefore tot3 is 2, 3 related to gap 3. Okay, I think I should hurry. So now the same thing you do for N3 and M3. It is just the same argument. Okay, N3, make a choice of a k tuple you know that in the central 5 copies, there are 3 misses. You choose one such miss. That gives you a partition of N3 into 3 parts. Those are the correspondences. Look at the first part, A1, A2. You know that this is a linear order of, is an ordered sum of greater than 2 to the 9 copies of gap 3, because of which A1 is 3, 3 related to B1. So therefore, there is a choice of B1, B2, and B1 such that the 2, 3 relationship holds. Likewise, the same thing holds here. And we have already established that tot 3 is 2, 3 related to gap 3. We put all these results together, and we utilize the composition property of the ordered sum. And that gives you a 2, 3 relationship between the top structure with A1, A2, A3 and the bottom with B1, B2, B3, which only means that because A1, A2, A3 were arbitrary, it only means that N3 is 3, 3 related to N3. And that gives you your result. Now, so with this, what we get is that sum total R is not equivalent to any pi3 sentence. You can do this for K, and you get that it is sum total R is not equivalent to any pi3K sentence, and therefore not equivalent to any pi3 sentence. That shows that Tait sentence is not even pi3. Okay, Coco, I must now ask you, how much time do I have?
I'd say 3 minutes, if that's possible.
Oh, all right. Sure, but okay, no problem. I had an intention to, so we have covered a good bit of ground. I think we have seen one result in its entire for all its details. I just wanted to present to you the generalization without going through any arguments. Maybe I'll just very quickly skim through it and get to the conclusions. Maybe in 2 minutes, let me try and do that. So generalizing Tait sentence, it's very easy. Okay, you just completely bootstrap this on the constructions. Okay, so this is the result that we want to show, that there is a sigma 2n plus 1 sentence which is extension closed but is not equal to any pi 2n plus 1 sentence in the finite, and it is expressible in Datalog. So once again, we look at the sentence, Datalog, and mk and nk. It's exactly the same thing, just lifted to n. Okay, the generalized sentence is such that the base case is exactly Tait sentence. Okay, and this is the inductive step. This is the base case for this. Okay, where you have relations R and S replaced with R1 and S1. And what you do at the nth level is, assuming that you have the n-1th level defined to you, you just construct analogous sentences with the important condition that the successor relation, which was earlier just the atomic predicate S, now is a formula. This formula is saying that Sn, which is an atomic predicate, is true, but it is true that U and V must induce a structure. U and V, the points that are there between U and V, must induce a structure which satisfies sum total R and minus 1. This is what the conjunction of these two is what you would regard as the successor relation. This is the generalized successor relation at the nth level now. Okay, with this successor relation now, you can define R total n in the same way, that you can just go from V to U, U to V using this sequence of successor n hops. Okay, that's all. That's the only edit that is there required to be made, and this is where the induction comes in. This is where you bootstrap. Okay, that's the relation. This can be expressed in first order logic. I will skip that. This has a Datalog program. I will skip that. The Datalog program is simply inductively constructed. It is exactly the same thing that we saw earlier, now lifted to this general n. Mk and Nk. So we want to do the same thing. We want to get a model of the sentence, a non-model of the sentence, such that there is a 2n plus 1k relationship between them. Okay, and here is what we do. The base case is again the Tait's example. So these are the structures that we just saw: L8, 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 G8, gap, and tot. So now you see that there's a 1, 3 coming in. So that was why the 3 was there earlier. That needn't be there. So far, this is exactly the same as what we saw earlier. At the nth level, what we are going to do is, assuming that you have the structures n and m defined for little n minus 1. Assuming that you have that, you are going to construct gap 3 and tot 3 at the nth level, okay, as the ordered sum of, first you construct this subroutine, which is n plus p3, which is taking 2 to the power 3 into 2n copies of np3, adding an Sn relationship between them, which will demarcate that this is a segment. This is a segment which has been demarcated with this Sn edge. Once you create this segment, you take ordered copies of these, and then that is one unit. Okay, those units become the endpoints of gap n3, and then you have once again 7 copies of n of these units with the central copy replaced with m. Okay, so this is very much like m treated like the gap and n treated like dot. Okay, sorry, yeah, that's right. Okay, and that's how we get these structures. And once again, you have m and n defined exactly the same way as you have gap structure, ordered sum of gaps with the dot in the middle, and so on. So this is exactly the same as earlier. And the claim that I'm making is that all of these can be shown analogously to what we saw. The sentence sum total Rn that we constructed is not extension closed in the infinite. You can construct a specific example showing that. MNK is a model of sum total R, but NNK is not a model. Tot is 2NK related to gap, and NNK is 2n plus 1 related to MNK. And that completes, that shows that no pi to n plus 1 K sentence is going to be equivalent to sum total Rn, but K was arbitrary, so therefore it's not equivalent to any pi to n plus 1 K. All right, so I think I'm here at the conclusion. I did that in like exact 3 minutes maybe. Okay, so those are the main results. Summarily, to summarize, this is what we saw in this talk, that we saw the Tait's example and we saw the generalization of this Tait's example. Okay, this is just a recap of what we have seen. No prefix class of first order logic. The takeaway from this talk is that no prefix class of first order logic is expressive enough to capture extension closed FO properties in the finite, and it is also not expressive enough to capture Datalog queries that are inside first order logic in the finite. That's the summary of this. The future directions are that the future directions are a natural question that would have come to your mind is that, well, maybe I've not given you enough time to ponder on the sentence sum total Rn that I constructed, but sum total Rn has a vocabulary which depends on n, because at every stage we are adding these new predicates Sn, Rn, and so on. So you're constructing more and more sentences with a larger and larger vocabulary. Can you have a fixed vocabulary which witnesses the failure of prefix classes in capturing extension closed properties in the finite? Okay, that is one question, a very natural question. Can you do that without increasing the vocabulary? Can you have a fixed vocabulary? That is one. Second, we are looking at these structures which are really ordered structures, but which are really ordered multigraphs. Yeah, we have binary relations, but we also have an order, but you have multiple binary relations floating around. Can we ensure that, can we try and get an example only for graphs? Only undirected graphs, maybe some colors, vertex colors allowed, but only for this particular setting can we show that prefix classes again fail to capture extension closed properties of graphs. After all, I began giving you examples of extension closed properties of graphs. So what happens to graphs for this particular result? Not known, but so far. So that's need to work upon that. But at least the first question is resolved now. The first question, there is an answer for that now, and you can show that there is a fixed vocabulary of size at most 4, possibly even 3. But at least with 4 predicates, all of which are binary, you can get the same result. Okay. But for the second question, we do not know yet, and it will be interesting to resolve this. It will have some kind of interest in the graph theory community, I would believe, and even generally to know the power of prefix classes in the context of graphs. So that will be an interesting question. All right, I think I'll stop on that.
Thank you. I'll unmute you all so we can clap. Yep. So let's thank the speaker. All right. Is there any question? So I can see one from Prabno. So I'll ask. Wait a second. Yeah.
So yeah, the models that you use to prove that it is not the models that you gave were large. So is there any result known for small models like?
Okay. Of course, for the result, this result is it is for just this particular result to go through, it is whatever model you constructed is fine, because that is the result that you're trying to show. The question of is a separate question now. Well, you want small models which will witness this. So, which means you want to say that if there is a distinction, which there's a counterexample, this distinction can be already be witnessed within a small within a bounded size. That remains to be seen. That's a very good question, actually, because yeah, we are utilizing the full power of ordered sums and so on. But maybe all of that is not required. I would think definitely that you can optimize on the sizes. Definitely an optimization of the sizes is there in the paper. I've given you a simple example to communicate the ideas, but that optimization in the paper is also not optimal. Could easily admit further optimization as well. Because after all, if you were to cumulatively look at M3, this is like one massive linear order. So much amount of linear order is not maybe required for showing the result. Maybe, but then the benefit of having these large numbers is that the proof becomes easy. Yeah, it is very simply compositional. Now, if you wanted smaller sizes, then you would have to try and do some other kind of an argument, or you would have to refine your compositional way of looking at things itself. So that is immediately not very clear how to do that and what these bounds would be like. But that's a very worthwhile question to think about.
Okay, thank you.
Okay, next question is from Anantha.
Yeah, Anta.
Did I unmute?
No.
Hi. Thanks for the nice talk. So I had a question which is about this gap plus. It seems that the construction seems to work without using the gap plus, right? So where do you use the gap plus?
No. See, okay, let's go back. The gap plus was where you ensured that there was sufficiently many copies. So, for example, let's see gap plus is here. Gap plus, yeah. Oh, I didn't. So that's a typo here. So that green that's there at the very end of M3 and N3, that must be a gap plus. Observe that if you didn't have the gap plus, then you have only 7 copies of gap in N3. Okay, 7 copies of gap in N3, but the amount of equivalence that you want is n comma k. That is not very clear now. With 7 copies alone, can you do n comma k for N3? That in fact there might be even a counterexample for this. Yeah. In fact, even at gap so let's look at just gap 1. I mean the first level. At the very first level, if you didn't have these magenta colored end points at the end, what you have is, let us say you have tot 3, which is a linear order of length 50 whatever 8 7s are 56, and then you have something similar there. Okay, but now you want to show 1-3 equivalence. 1-3 equivalence probably might be easier, but you can see that already as you keep going further, you will start to run out of enough copies. Yeah. Yeah. I think you will run out of it when you go to sufficiently large n. You need this particular thing. It is because of this padding with sufficiently many copies that you have sufficiently many copies. Otherwise, you would run out of copies. I think you can. It's a good question to try and explicitly construct counterexample for this, and it definitely is. You can construct one. I'm very sure. So you need that amount of copies.
Okay. Thank you.
Sure. In fact, look at this way. If you didn't have the copies systematically at all levels, then you are really looking at each of these 7 copies that are there of NP3 is itself composed of only 7 copies of the lower level and so on. Eventually, it will be a very small number of copies that you will eventually have. So the linear orders that you'll be constructing will eventually be just some multiple of 7. Yeah.
Okay, so I was thinking more like if there is k, some 2 to the k many copies should be enough. So this is really adding more. So it's like adding 2 to the k copies again at the beginning, at the end.
You would require that. I mean, because your equivalence is nk, so the total number of points that you're choosing is n into k.
Yes.
It's an n round game, but
Right.
n round game you're choosing a k table, so you're choosing nk points. So if you were to use the classical result about linear orders, your m for m equivalence is nk.
Okay.
So you would need enough padding. Maybe not so much padding. Sure, it might be, but you would need some padding which is exponential. Otherwise, if you didn't have the padding systematically at all levels, then you're just talking about some multiple of 7, which might be insufficient. But yes, you can optimize. Yeah, that is true. but I don't think you can get sub-exponential. That's a good question itself. Can you get sub, which is related to the first question?
So, so for instance, in this current slide, so the gap n comma 3. So let's say that is why you have this 7 copies. If it was some n comma k, wouldn't 2 to the k many copies of Sn suffice instead of having n plus?
Yeah, this is, yeah, I would have picked 2k plus 1. This is,
Right.
yeah, so this is just sufficient enough so that when you pick k elements, you'll miss some, many things. You will miss already in the central k plus 1 in the central k plus 1 segment itself. You will miss a lot of things. Yeah. So surely you do not need so many copies, but in the paper, of course, I'm giving you a simple bound, but in the paper we have a slightly improved bound. But I don't know whether the bound can be drastically reduced. In particular, I don't know whether it can be sub-exponential. That's a good question in itself. Can you give the proof via the same strategy, but having sub-exponential sized structures, M and K? That will be a very interesting question to investigate.
Okay.
Yeah, but at the moment, yeah, sure.
Sorry. Okay, let me see. So far, okay. Finally, Thomas might have some fun question.
Yes. Am I unmuted?
Hi, Thomas.
Hi. It's just have you calculated the size of M55?
Have I calculated the size?
No, but I even have a serious
On the
question.
computer, you're doing some calculation there. You seem to have encountered some humongous number, is it?
No, I give up.
Yeah, but no, I have not calculated. I can give you a reconciliation, but
yeah. But a more serious question. I did not understand the point of your future direction question number 1,
sure.
Because it seems to me that this is what you already solved, but maybe I missed something. Because you say the for that vocabulary of size at most 4, isn't this what you did for size 2 actually, or 3, depending if you count the
right. So maybe because maybe because I rushed through, that's why you didn't get time to see this. But see, if you were to go back, yeah, here is a sentence. So this is an inductively constructed sentence. The very first level of it has 3 predicates. This is Tait's sentence. Yeah, so there are 3 predicates here. But now when we go further to n, we are adding 3 more predicates here. I wish I had a pointer. I cannot. But if you observe the second line here, it says the vocabulary sigma n minus 1 union 3 more predicates.
Okay.
Yeah. So these 3 predicates. So that Pn is what is colored as orange. Pn is an unary predicate. It is what is representing this orange color. Okay. Otherwise, the vertices would have been colored green, but this color is orange. And the predicate Rn and Sn, you see they're utilized. You see the way they're used in successor n. That is somewhere in the middle of the page. Successor n contains Sn, right? And likewise, R total n contains Rn, which means these 2 predicates are non-trivially being used in the nth level. So you have gathered, and there is some total Rn minus 1 also appearing, which means it itself has gathered its vocabulary of sigma n minus 1.
All right. And do you assume as well that this S is a successor? Sn is a successor the same way S1 is?
No, that's what.
No.
Successor.
Okay.
The new successor relation is now defined as this composite. It is defined as this Sn, which is atomic, conjuncted with the previous sentence, the sentence at the n minus 1th level that it constructed. Okay. So that is the new notion of successor now.
Okay.
Yeah. So that's where you find that this whole thing is, so if you want to construct the model, and that's why that also shows up, when we constructed these models, we had these previously constructed models as substructures inside our new MK and NK, right? Because MK and NK were composed of gap and taut, but gap and taut itself were composed of MK minus 1 or n minus 1K and n minus 1K. Yeah. So therefore the vocabulary is indeed growing, indeed linearly with n. It's 3 times n. Okay, but now the question is, well, if you fix the vocabulary, then is it the case that prefix classes, still fail to capture extension close properties of fixed finite vocabulary, and that we are able to show. And in fact the idea is very simple, but I will not go through it. The essential idea simply here is that these colors, right, these PN, etc., you just add in gadgets which are definable gadgets which will serve as PN. So PN can be seen as a unitary relation. Yeah, it's just a predicate, but you can also define a unitary relation using a certain gadget which serves the function of PN. So that way you can get rid of these extra colors PN. And the way to get rid of Rn and Sn is to always observe that Rn always relates to orange points. Sn also always relates to orange points. Right? So you might as well keep in one copy one relation called R, which relates to orange points, but the orange points will themselves identify the level. Yeah. So that's sufficient. You identify the level using the orange points, and then you just use the same predicate R and S. So that you can get rid of all these R and Sn in this way. And the way you get rid of the orange colored points is just by using an interpretation, by defining it, by definably getting PN.
Okay.
And that gives you 4 predicates, but I think you can get it down to 3, but that requires some work. But the question is, can you get it down to 1? So that'll be interesting. So in fact, the question that is there, this open question that is there, even for directed graphs, can you show that prefix classes fail to capture extension close properties of ordered graphs? Of directed graphs, sorry, directed graphs. That is also a question which will be very interesting.
You just add some loops somewhere and you'll be fine.
So I must mention in this context, that, well, I was thinking about all of these things, and so one can naturally ask, what happens to just classical Los-Tarski theorem? Tait's example that we saw contains 3 binary predicates. Actually, I have presented 3 binary predicates, but you can do it with 2, okay, using the same kind of optimization. So Tait's example uses 2 binary predicates. What happens over graphs? This was a question that I had actually raised in ICLA last year, and that question has only recently been answered. So Flum and Chen have a paper in which they have shown that Los-Tarski theorem fails over graphs, just undirected graphs. It is not true, which means existential sentences cannot capture extension close properties of undirected graphs. But that is only so that is a result. So that is an important result that is only recently done. But it still does not mean that well, that is only the existential fragment, that is just sigma 1. Maybe it is the case that extension close properties of undirected graphs are definable inside a sufficiently large prefix class. Yeah. So that question still remains open. So we want to settle that. My hunch is that it is in the negative once again. Prefix classes, even over graphs, cannot be powerful enough to capture extension close properties. So that result would be the result to attempt for. That will be a generalization of even the existing result. And yeah, that will be the strongest result that, but at least with respect to prefix classes, that will be the best thing to have.
Okay, actually there's one other question. I think it's going to be the final one.
Yes.
And that's from Alak, and I'm going to read that. So the question is, have you had any success in lifting this argument to your more general definition of K, hereditary or extension, or even one hereditary, one extension?
Nice. Very good question. I'm glad that who's I don't know who's asked the question, but I'm glad
that's from Alak.
Alak, I see. Oh, Alak. Okay, hi. So thanks for that. I'm glad that you have an interest in K-hereditary properties. Indeed, that will be the next step to try and do that. Of course, all of these hereditary properties are also K-hereditary. They're just 0 hereditary already. So therefore, they are K-hereditary for every K. Okay. So explain, having failure results already for hereditary properties is naturally, is also a failure of K-hereditary properties. What we would like to see is a truth of Los-Tarski theorem, okay, which would be saying that existential fragment is sufficient to capture extension close properties, and then we want to try and see that the generalization does not hold of K-hereditariness. So here, yes, so this is indeed true actually. So if you look at bounded tree-width graphs, in fact, if you even look at, so the generalization, since probably, for the others, basically, I had defined my thesis a generalization of hereditariness. So extension closure, if you were to look at it in its negation, in its complement form, yeah, extension closure is basically saying you start off from a graph, you extend it, you preserve the property. If you look at the complement of it, you're saying that you start off from a graph, you go below it, look at an induced subgraph of it, then you preserve the property. So this is hereditariness. So you can define a more general property than hereditariness, which I call K hereditariness, which, for example, if you have a dominating set in a graph, yeah, so you have K vertices such that every other vertex in the graph is either one of these K vertices or it is adjacent to one another. So this property is not hereditary. It's very easy to construct an example to show that this is not hereditary, but it is K hereditary, which means that if you were to take these K points which constitute the dominating set, then if you were to take any induced subgraph always containing these K points, then even the induced subgraph continues to have a dominating set of size K. Yeah. So K hereditariness is a more general property than hereditariness. And in the same way as hereditariness is characterized using universal sentences via Los-Tarski's theorem in the infinite, you can show that K hereditary properties are captured using exists K for all star sentences. K existential quantifiers universal and then universal in the infinite. In the finite, this result fails. The uniform result that K hereditariness is equal to exists K for all star, which in the special case when K equal to 0 is like hereditariness equal to for all star. That's Los-Tarski's theorem. So K hereditariness is equal to exists K for all star fails in the finite, obviously because it case fails already for K equal to 0, but you can show this failure at every level. In special cases, for example, Anuj, Martin Grohe, and Albert Adfried, they have these results where they look at structurally defined classes like bounded tree width, bounded degree, and so on, and they show Los-Tarski's theorem is true over these classes. Now, the natural question is what happens to the K hereditariness equal to exists K for all star correspondence over these classes? And you can show that it is false, even for K equal to 2 and beyond, at every level greater than 0. At every level greater than 2, greater than equal to 2, this correspondence fails. Okay. So here is an example where you do have Los-Tarski's theorem holding over a graph class, but you do not have the generalization holding over the graph class. So now for those cases, that's a nice question now. For those cases, is it the case that, so I was just thinking about this actually, is it the case that K hereditary properties of bounded tree width graphs, they are not expressible by exists K for all star, but are they expressible via some higher prefix class, or even if we relax the number of existential quantifiers, even we say that it's a K hereditary property, can it be expressed using a sigma 2 sentence? That'll be something to investigate. Yeah. Maybe the correspondence with K is making it too tight. If you allow for L greater than K, L which is sufficiently large, then maybe it is expressible. But is it so? Is a very natural and a very nice question to ask. And I do have that in one of my things to do.
Great.
Yeah. So thanks.
Okay. Let's wrap up. So I'm muting you all. Okay. Yeah. Okay. So yeah, let's thank the speaker again. Thank you. Okay, now I stop recording.